Alright, so I'm going to talk about continuous time Fourier transforms and their applications and, taking inverse Fourier transforms and all the fun stuff. Alright, so here we begin. We're asked to compute the Fourier transform of x of t equals the summation from k equals 0 to infinity of 1/2 to the k delta of t minus k. So what we're going to do here is just take the basic formula of taking the Fourier transform, which is just x of j omega equals, the integral from negative infinity to infinity, x of t e to the minus j omega t dt, which there it is right there. So basically all you're going to do is put whatever x sub t you have and you place it in right there. And so this is how it turns out to be. But so notice here that there's only one thing that depends on the t itself, which is just a delta. So you can pretty much remove the summation from k equals 0 to infinity of 1/2 to the k outside of the integrand and evaluate delta of t minus k times e to the minus j omega t dt. So basically you're just going to implement that, and notice you're going to have to use a sifting property here. So if you move on to the next portion of this, you get here, and then here's the sifting property implemented, which just tells you that the integral from negative infinity of delta of t minus t naught e to the j omega t dt gives you e to the minus j omega t naught, right? That's basically the sifting property. Whatever you sift in the delta function goes on your exponential, e to the minus j omega t naught. So using that knowledge, you end up with summation from k equals 0 to infinity of 1/2 e to the minus j omega k, right? 1/2 to the k times e to the minus j omega to the k. What I didn't do here was put them all under one one formula, basically one expression, but you could have done that and recognize that this is a geometric sum, k equals 0 to infinity, and the way to evaluate a geometric sum is doing the expression raised to the lower bound, divide that by 1 minus the expression itself. In that case, the expression is 1/2 e to the minus j omega, and that's the final answer. Now here, we're dealing with trying to find the inverse, or actually the Fourier transform of x of t equals t e to the minus magnitude of t, right? Now notice here, this magnitude of t kind of makes things a bit complicated. So the first approach you'd want to do is just use the basic formula itself, which is x of j omega is equal to, the integral of negative infinity to infinity x of t e to the minus j omega t dt. And this, of course, if you put it into if you plug in x of t, you get this expression, right? Notice here, you'd have to split this expression up into two different parts because of that magnitude. So you're going to have one going from negative infinity to 0, which deals with negative t's, and the other one going from 0 to infinity, and that deals with positive t's. So to formulate the way we got t e to the 2t was plugging in negative t, and that gives you a positive 2t. And here, you have a positive t, you just plug it in, and you end up with that expression. Now that is a lot of math to do, so I came up with an alternative, which is much simpler. So here you can recognize that x of t is just differentiation in frequency, right? Which is x of t is equal to j d omega x of j omega. So you're basically just multiplying j times the derivative of x of j omega. Now you need to figure out what your x of t is, right? lucky for us, we do have a property for the Fourier transform of x of t equaling e to the minus 2 magnitude of t. Now, what people usually mess up on is, trying to think it's multiplication, but it's not multiplication. So just use your properties. So x1 of j omega would equal 4 over 4 plus omega squared. This would be your property, right? Using your property. Now, what you want to do is take the derivative of this, right? Because that's what we're looking for. That's the final step. So j times d over d omega of 4 over 4 plus omega squared. This gives you your x of j omega, which is equal to minus 8 j omega over 4 plus omega squared, all squared. And that's the answer to this problem. Now here we have a signal, which is e to the j pi t times sine pi t over pi t, convolved with sine 2 pi t over 2 pi t. Now, keep in mind that convolving in the time domain means multiplication in the frequency domain. So what you would need to do is, recognize first of all that these two signals themselves are, well, you're convolving two different signals. So what you want to do is first initialize x1 of t to equal sine pi of t over pi t, and x2 of t is equal to sine 2 pi t over 2 pi t, right? Now, by using your properties, you can figure it out. But e to the j pi t is just a shift. So that you can cast aside for now. Now, x1 of t is equal to sine pi t, and x2 of t is equal to sine 2 pi t over 2 pi t, right? Now we want the inverse of, we want the Fourier transform of those. Using our properties, we know that the Fourier transform of sine pi t is a sinc function with the height of 1/2, where the magnitude of omega is less than pi, and 0 for the magnitude of omega greater than pi. And using our property for x2 of t, x2 of j omega is equal to 1 for the magnitude of omega less than 2 pi, and 0 for the magnitude of omega greater than 2 pi. Now, what you want to do is initialize a third signal, right? Which is going to be the multiplication of x1 of j omega times x2 of j omega. And notice when you do multiply these, the 2 pi doesn't carry down because it's limited by that pi from x1 of j omega. So x3 of j omega will be equal to 1/2 the magnitude of omega less than pi, and 0 for the magnitude of omega greater than pi. And this x3 of j omega resembles x1 of j omega. Even though it is a bit kind of odd to think of it that way, but for the math's sake, just keep that in mind. Now, x3 of j omega is equal to x1 of j omega times x2 of j omega. That we've established. Now, what we want is the actual x of t shifted by that pi, right? So, x of j omega is going to equal x3 of j omega minus pi, because we're shifting it by the pi e to the j pi t. And that's the expression we end up with once we shift it. Now, once we do shift it, you have to keep in mind when you're subtracting it with the shift, that means you're shifting it to the right. So x of j omega will be x3 of j omega shifted by pi to the right. Now notice that the range of this goes from negative pi to pi. So if you add pi to both sides, you get 0 on the left side and 2 pi on the right side for x3 of j omega. So x of j omega here will go from 0 to 2 pi with a height of 1/2, and that is a visual representation of how it looks. And this is pretty much all you need for this problem. It's the correct answer.
Hey everyone. Okay, so today we are going to go over quiz 4 from Ecen 314. This is a 30-minute quiz over convolution, 2 questions. So, first question is let x of n be denoted by this function right here, and h of n denoted by this function right here. Compute and sketch y of n, which is defined as the convolution between the two. So the way we do convolution is we change these independent variables n to a k, and then we flip one of them. I usually do h of n or h of k to give us an h of negative k, and then we shift it by a value of n either to the left or to the right, and then and that's how we perform the convolution. So this is a discrete time, so this is a little bit easier. So what I usually like to do is I like to draw h of negative k after flipping the independent variable and flipping it over the y-axis, and that way I can line it up with my x of k and see a little bit more easily like how the bounds are affected. So when as you can see, when h is, or when we shift it by a value of n, right, let's less than 0, this graph will be shifted to the right or the left by 1, right? So these two signals right here will not overlap, and therefore y of n will just be 0. So for starters, let's write out the definition of the convolution in discrete time. Right. So that is the definition of discrete time convolution. So when we convolve two signals, this is the result. So, and now I like to list out my bounds. So when n is less than 0, right, the shifting value, y of n will equal 0 because the signals will not overlap. And now let's see what else we get. So when n is equal to 0, they only overlap at one place, right? They don't overlap at two places. So we get 2 times 1, which is just 2. So n equals 0, y of n equals 2 times 1 equals 2. Perfect. Alright, and then, so now we have when n is greater than 0, but between greater than 0 but less than or equal to 2, right? Because when this is 2, it'll be, this will overlap with this and this will overlap with this. But when it's 1, this will overlap with this and this will overlap with this right here. So when n between 0 and less than or equal to 2, y of n will equal the sum from k minus 1 to n x k h of n minus k. So, and this is kind of a discrete time one, and it's fairly simple to kind of see it. There's not a lot of values, so we can just go ahead and compute it. So when n is equal to 1, right, so it's going to be shifted to the right by 1, so this and this will overlap, this and this will overlap. So we have 1 times 1 is 1, 2 times negative 1 is negative 2. So when we add those together, that gives us negative 1. So when n is equal to 1, we have y of n equals 1, negative 2, plus 1 times 1, negative 1. And then when n is equal to 2, 1 times 2 is equal to 2. 1 times negative 1 is equal to negative 1, which gives us 1 when we add them together. So y of n equals 2 times 1 plus 1 times negative 1, which gives us 1. Alright? And then the next bound, when n is equal to 3, right? 3 minus 1 gives us 2, so that'll be, so only this will overlap with this last value right here. So negative 1 times 2 is negative 2. So next bound, n equals 3, y of n equals 2, negative 1, negative 2. And then next one, when n is greater than 3, right, these no longer overlap. Like let's say this is 4, right here. When this is 4, 4 minus 1 will equal 3. So those two signals will no longer overlap, and y of n will be 0 again. So n greater than 3, y of n equals 0. And then we can use our values to sketch y of n. So say 0, 1, 2, 3. So at 0, less than 0, 0, so we don't really care about it. At 0, get a value of 2. At 1, we have a value of negative 1. At 2, we have a value of 1. And then at 3, a value of negative 2. So 2, negative 1, 1, negative 2, greater than 3, 0. So here's y of n right here. And then we can write this as a sum of delta function, so 2n plus negative 1 delta, here, you know, I should just write that as a minus delta n minus 1 plus delta n minus 2 minus 2 delta n minus 3. And that is the result of the convolution. And there we go. Alright, so now question 2, another convolution one. X of t is given by that function e to the negative t times those sum of u functions, unit step functions, and h of t is equal to the sum of unit step functions. And then y of t is defined by the convolution of x of t and h of t. And we would like to specify the intervals in the function within the interval. So we don't have to sketch it, we just got to compute the intervals and find out the function within those intervals. So I like to, like I said, I like to draw h of negative tau in this case. And so we see that when t is less than 0, these will not overlap, right? When t is less than 0, this will be shifted off by some value over here, and they just don't overlap. So we know that when t is less than 0, then we know that y of t will equal 0. So question 2, when t is less than 0, y of t is equal to 0. Okay. And then now, when it is greater than or equal to 0, and or just whenever it's greater than 0 and greater than 1, or between 1, right? Because this has a width of 1, and so does this. So they will overlap just a little bit. So when this is greater than 0 but like less than 1, let's say, they'll overlap a little bit. So like this will be about right here, and so that bottom bound will always be this 0 function right here, and it'll go to however much we shift it by, right? Because this is 0, so we go from, when we add t to that, it just some value of t. So when we have 0 less than t less than 1, y of t, and we'll say we'll use the definition of convolution in this case, which is the integral from your upper and lower bounds. So we'll say t1 t2 of x of tau times h of t minus tau d tau. So in this case, our lower bound will always be 0, and then it'll go to a value of t. And then when we multiply the functions, right, this only has a height of 1, right, because it's just made up of 2 unit step functions. So when we multiply it, h of t minus tau is just 1, so we just get x of tau, right? So we just integrate that function, x of tau. So x of tau d tau, and this is equal to 0 to t. X of tau is given by e to the negative tau d tau, and we don't have to worry about those unit step functions because those are already included when we define our bounds. And so you can integrate this and get that we get 1 minus e to the negative t. And there we go. Alright, but we're not finished yet. So now when we have when a value of t, the shift value is greater than 1 but less than 2, right? So when we shift this over by 1 at the minimum, these two will be completely overlapped, right? But if it's greater than 1, this value, because it's at negative 1, let's say it's like 2, no, let's say it's like 1.5, then this will be shifted to a value at 0.5 right here, and some of this other, the rest of the signal will be will not overlap with this. So in this case, our bounds are a little bit different. So when we have 1 less than t less than 2, y of t, use the definition of the convolution. So our lower bound in this case will be t minus 1, right? Because our lower bound is always changing, right? Because when we add a value greater than 1, this will become our new lower bound because it will not overlap with let's say it's 0.5, or let's say our shift value is 1.5, so they overlap at this 1.5 or the 0.5 value. The only overlapping part will be this right here. So this region, so our lower bound from the integral is this right here. And so we can describe that for any value greater than 1 for t to be t minus 1, right? And then the upper value, right, that's not going to change. That'll just be 1 because the other signal will be off over here and they won't overlap. So the upper bound will be 1 in this case. So, and then e negative tau d tau, and then we get something like e to the negative t minus 1 minus e to the negative 1. And then finally, when we have when t is greater than 2, right? So let's say it's let's just say it's 2.1. So 2.1 minus 1 is 1.1. So this bound right here will be at 1.1, which is right past this 1 value. So then the signals will no longer overlap, and therefore, so when t greater than 2, y of t is equal to 0. And there we go. The functions within each interval. And we have performed the convolution. Hey everyone, so today we will be working exam 2 from spring 2019 for Ecen 314 Signals and Systems. This is about a bunch of Fourier series, Fourier transforms, things like that. And so this is the first question we have for the exam. Consider a continuous time signal x of t shown below with fundamental time period t naught equals 2. There's a sketch of the graph, the function right here, e to the negative t from 0 to 1, and then 0 between 1 and 2, as you can see, and just repeat. And then here each part of the questions, find the fundamental frequency, let x of k denote the Fourier series coefficients, compute x of 2, and write the real and imaginary parts clearly. Then part C, light passing through a prism was used as an analogy to explain the Fourier series in class. Briefly explain this analogy. Alright, so let's get to it. So, part 1a, find the fundamental frequency. Well, we know the fundamental frequency omega naught is given by 2 pi over t naught, and t naught was equal to 2, so we know omega naught is equal to pi. Boom. So that is part A. And part B is let x of k denote the Fourier series coefficients, and we want to find x of 2. So we are given this nice little packet of transforms and definitions of integrals. So we have a continuous time, and we want the Fourier series coefficients, so we will be using this integral right here, x of k over 1 over t, is equal to 1 over t integral over the fundamental period, or any period of x of t, e to the negative jk omega naught t dt. So when we do this, we get an integral of something like x of k equals 1/2 integral 0 to 1 of e to the negative t, e to the negative j, k omega naught t dt. So, when we perform this integral, we get something along the lines of 1/2 minus e to the negative 1, e to the negative j, k omega naught, all over 2j k omega naught plus 1. But you want us to find x of 2. So x of 2, we just plug in 2 for k, right, is equal to, so 1/2 minus e to the minus 1, e to the negative j 2 pi over 4 pi j plus 1. And so we can simplify this a little bit by just realizing that e to the negative j 2 pi is just equal to 1. So we get something like 1/2 minus e to the minus 1, 4 pi j plus 1. But this is still not quite right because we have to break up the real and imaginary parts. This is real, so there's not really breaking up anything there. This is complex, and so we can break this up into its own real and imaginary parts. And the way we do that is multiply by the conjugate of this. So we'd multiply both sides of the fraction by 4 pi j minus 1. And this should get us something along the lines of 1/2. Oh, my bad. 1/2 plus, no, my bad. 1/2 minus e to the minus 1 over 16 pi squared plus 1 plus 4 pi e to the minus 1 times j over 16 pi squared plus 1. And that is our final answer. And then for part C, I'm not really going to write that out because that's just kind of an explanation. But for part C, when describing using light passing through a prism to describe Fourier series, light is when it passes through a prism, you can see that we get this sort of rainbow effect ranging from red to purple, and this can be used to describe light as a combination of a bunch of colors of different frequencies, and that's exactly what Fourier series are. Is they break up signals into different components taken of integer multiples of the fundamental frequency, and we can use these Fourier series coefficients to match the signal, and that's basically the answer. So there's question 1. Hey everyone, so today we'll be going over question 2 from Exam 2 Spring 2019 for Ecen 314 with Dr. Krishna. So, a continuous time periodic signal x of t has the following Fourier series coefficients, and there's our given expression. Parts A, B, and C. If the fundamental time period is t is equal to 1 over 100, find x of t, simplify, and write your answer in terms of cosine and sine functions. If the fundamental time period is t is equal to 1 over 200, find x of t. And part C, find the power of the signal for the signal found in part A. Alright, so the way we do this is we go back to our nice and handy dandy packet, and we want to find x of t. So we can write x of t in terms of the Fourier series coefficients and e to the j k omega naught t, right? So when we do this, so we get an expression for x of t, which equals the sum over k for x of t, or x of k, my bad, e to the j k omega naught t. So when we do this, we get, so our expression was for x of j omega, or x of k, negative 2 delta k plus 4, and I'm going to multiply that by e to the jk omega naught t plus delta k plus 1 e to the jk omega naught t, and we're just going to keep doing this until we run out of jk terms. Ran off the edge there a little bit, but that's alright. Alright, so what's nice about this is these each all have a delta term, so we can simplify this a lot easier, and using properties of delta functions, we will get something along the lines of e negative j 4 omega naught t, right? This is delta k plus 4, so that just replaces this function k with a negative 4. And same thing for all this, except in this case right here, we get k is replaced with a negative 1, so e to the negative j omega naught t plus, and then we have a k minus 1 in the delta, so we get k, we get a positive 1 replaced with k, e to the j omega naught t plus 2j positive 4 e to the j 4 omega naught t. Alright, and this should start to look familiar in a way, and it start to get into that form where we can write it in terms of sine and cosine functions, which is exactly what we want. So I'm just going to break this up a little bit, write it in a little bit different way. 2j e to the j 4 omega naught t minus e to the negative j 4 omega naught t plus e to the j omega naught t plus e to the negative j omega naught t. And I'm just going to play with these coefficients right here to get it in the form that we want, so we can substitute in our sine and cosine functions. So the way we do that is we'd multiply this by 2j, and this by 2 over 2, and this would be 2j over 2j. So we get minus 4, oh, no j there, over 2j e to the j for omega naught t minus e to the negative j for omega naught t plus 2 over 2 e to the j omega naught t plus e to the negative j omega naught t. And so now this should look pretty familiar. So 1/2 times e to the j omega naught t plus e to the negative j omega naught t is simply cosine omega naught t. So then all this right here is 2 cosine omega naught t. And then this right here, 1 over 2j times e to the j for omega naught t minus e to the negative j for omega naught t is simply sine of 4 omega naught t. So with the negative 4, you get minus 4 sine 4 omega naught t. And we just add them. And so do we have omega naught? Yes, we do, because we know the fundamental time period is t is equal to 1 over 100. And so omega naught is equal to 2 pi over t, which gets us 200 pi. And so we plug it in to our function right here, and we get 2 cosine 200 pi times t minus 4 sine 800 pi, right? 200 times 4, 800 pi t. And there's our x of t. And then for part B, it wants us to replace t with 1 over 200. So omega is equal to 400 pi now. And so we plug omega in for these values, or for these functions right here, and we get 2 cosine 400 pi t minus 4 sine 1600 pi t. And there's our new x of t. And finally, for part C, it wants us to find the power of the signal for part A, which is this one right here. So how do we do that? Well, we refer to our packet, and we can find that okay, it doesn't have it, but that's okay, because if you remember, we can use Parseval's theorem, and we know that the average power for a periodic signal is just equal to the magnitude of Fourier series coefficients squared. So then, if we go back to the original question, or let's just scroll up to the top. So we got negative 2j, 1, or actually we should be looking at this one right here. We got negative 2j, 1, 1, and 2j. So when we take the magnitude and square all those, we should get 2 squared plus 1 squared plus 1 squared plus 2 squared. 2 squared is 4, 4 plus 4 is 8, 1 squared is 1, so 8 plus 2 is 10. And there we go. Hey everyone, so today is question 3 of exam 2 spring 2019 for Ecen 314. So consider the time signal x of t shown below given by this one right here, and then we have x1 of t given by this, and we only are given things for x of t right here as the function is equal to t from 0 to 1 and then 0 elsewhere. And we have here the Fourier transform of x of t is given by x of j omega is equal to e to the negative j omega over omega squared plus e to the negative j omega over negative j omega minus 1 over omega squared. And then a and b, let x1 of j omega be the transform of x1 of t shown above. What is x1 of j pi? And then part b is what is the integral negative infinity to infinity of x1 j omega e to the j1 over 4 omega d omega. Okay, so now let's get into it. Part A. Okay, so we want to find x1 of j pi. So to do that, we should probably find x of j omega, x1 of j omega. So looking back at the signal, how can we write x1 of t in terms of just x of t, right? So if you notice, we can write x1 of t as x of t, right? This is the x of t plus x of negative t, right? Because that's what this is. Right? And we don't have to worry about overlap because they're both 0 at 0, so they're not going to add on top of each other like that. So we can just write x1 of t as x of t plus x1 of t equals x of t plus x of negative t. So then so we already know the Fourier transform from x to t, right? So when we take the Fourier transform, x1 j omega is equal to x j omega, right? And the Fourier transform is linear, so plus, and then the transform of x of negative t. So we go to our packet, and we can find the time reversal property for x of a signal who's flipped across the y-axis. So we get that the Fourier transform of x of negative t is x of negative j omega. So this will become x of negative j omega. And they gave us the Fourier transform for x of t, x of j omega, right, which was given by this expression right here. So basically, we just take this and then add it to x of negative j omega, right? And so we just replace what we can with a negative. So like for these squared terms right here, that negative is not going to affect that. The squared will just go away, or I mean, the negative will just go away. But for here, like e to the negative j omega, this will become a positive, right? Because we're replacing it with another negative, so a negative and a negative will become a positive. Same thing for right here and for right here. So we have this part, which is e to the negative j omega, omega squared, plus e to the negative j omega minus j omega, 1 over omega squared. Now plus, so we replace this with the negative j omega, this j omega, so we get e to the j omega over omega squared plus e to the j omega over j omega minus 1 over omega squared. And that is x1 of j omega. And now we want to find x1 of j pi. So basically, wherever there's an omega, we just plug in a pi. So when we plug in a pi for each one of these, so if we plug in a pi right here, that's e to the negative j pi, which will actually just give us a negative 1. So we get minus 1 over pi squared. Same thing here, we get a negative 1 over a negative, so we get plus 1 over j pi, my bad, and then minus 1 over pi squared, and then e to the j pi will still give us a negative 1, so we get minus 1 over pi squared plus negative 1 over j pi minus 1 over pi squared. So if you notice, this term and this term will go away, which is very convenient because those are the imaginary parts. And then we just add this all up. So negative 1 pi squared plus negative 1 pi squared plus negative 1 pi squared plus negative 1 pi squared over pi squared. And that gets us negative 4 over pi squared. And that is 3a. Now for 3b, it wants us to evaluate the following integral: x1 j omega e to the j 1 over 4 omega d omega. So this should look fairly familiar, and if you notice, going back to our packet, that this is the inverse Fourier transform, just without the 2 pi. Right? Very similar, but as we see, t is replaced by a 1 over 4. So this actually gets us 2 pi times x1 evaluated at 1/4. Alright, and the 2 pi just comes from the definition of the inverse Fourier transform. We multiply both sides, we get 2 pi x of t, and then we get that integral. So 2 pi x1 evaluated at 1/4, and we know that in that region it's just x of t. So and x of t is just t between 0 and 1. So t is 1 over 4. So x1 of t is just 1 over 4 pi over 2. And there we go. There's question 3.
Now here you have a similar problem like the previous one we did a couple of minutes ago. Now here you have e to the minus j pi t, right? Now you're going to be shifting it to the left, and you have these two signals again, pretty similar but a bit different. Now it's sine of t over pi t. Notice here omega will be 1 for that first signal. Second signal, omega will be 2. If you look at the form of a sinc function, you can pretty much figure out what the bounds for omega will be. So again, convolving in the time domain means multiplication in the frequency domain, right? So what you want to do again is initialize your x1 of t to equal sine of t over pi t, and your x2 of t to equal sine of 2t over pi t, like so. Once you've done that, what you want to do is find the Fourier transform of these, and using the properties like we did in the previous problem, this is pretty trivial. And remember, again, convolving in the time domain means multiplication in the frequency domain. It's very important. Saves you a lot of work. Now, what we want to do is the same technique again, make x1 of j omega times x2 of j omega to equal to x3 of j omega, and that will make things a bit easier to deal with here when you have multiple variables. So you could just shift the final answer. But so x1 of j omega, again, using your properties, is equal to 1 for the magnitude of omega less than 1. So this means it's going to go from negative 1 to 1. And x2 of j omega is going to equal to 1, where the magnitude of omega is less than 2, which means it's going from negative 2 to 2. Now, x3 of j omega, like we did in the previous problem, it's going to take the form similar to x1 of j omega, because the range is going from negative 1 to 1. Anything outside of that will automatically go to 0, because you're multiplying two functions that the bounds don't match up. So here you have your expression for x3 of j omega. Now, the last thing you want to consider here with this problem is to shift it now. And like we said, if you want to shift it to the right, you have to subtract by pi. But here we're shifting it to the left. So you add pi, right? Hopefully you guys already know this little trick. So basically all you're going to do is add pi to your expression of x3 of j omega, which will potentially change the bounds. And your new bounds will be from negative 1 minus pi and omega in the middle, and to 1 minus pi. You're shifting it to the left by pi. And that's pretty much the solution for this problem. Alrighty, now here you're asked to find the inverse Fourier transform of x of j omega equals to 1 over j omega times j omega plus 2 minus pi delta of omega. Well, this doesn't look like any of the properties we know. So the natural thing to do here would be, use the basic formula that we've been taught. If you want to find the time expression of this, right? So you would do something like x of t is equal to 1 over 2 pi integral from negative infinity to infinity times x of j omega e to the j omega d omega. And that seems like the most logical step to do if you were faced with this problem, right? Maybe you could simplify to something simpler. Well, turns out it doesn't really simplify to anything that much simpler, because you end up with 1 over j omega times j omega plus 2 going from negative infinity to infinity. And that expression itself evaluates to 0, right? And then you have this negative infinity to infinity pi delta of omega, which probably gives you an expression, but since this evaluates to 0, we know our bounds are probably not correct. And if you're working on a problem like this one on an exam, you probably don't have the time to actually go through and try to figure out the bounds on this problem. So the most basic thing you can probably try to do is think through it and realize that 1 over j omega times j omega plus 2 takes the form of a partial fraction decomposition technique that we know. This is where you can split it up into two expressions being added together. Say a over j omega plus b over j omega plus 2. And basically what you want to do is find the coefficients, right? Neat little trick. And let's find these coefficients. So 1 is equal to a over j omega plus 2 plus b times j omega. And what you want to do here is solve for the coefficients, so you can express this expression into two different pieces. And once you solve for a, you get a equals 1/2, b equals negative 1/2 by setting j omega to specific values. And you end up with x of j omega equaling to this expression here, this nice expression that you can probably figure out by doing some math techniques. And notice here that 1 over j omega plus 1 half over j omega plus 2 is a property we know. We know the inverse Fourier transform of this. Using our properties, we know this equals to something very familiar, which equals negative 1 half e to the minus 2t u of t. Just by using our properties, we got that taken care of. Now, we want to deal with this 1 over 2j minus pi delta of omega. So what are we going to do here? Well, you have to realize that this resembles a property that it's on a table. It's on the Fourier transform tables. This resembles a unit step function, which is equal to 1 over j omega plus pi delta of omega. Now, it's sort of familiar to ours. So what do we do here? First, we take care of this 1 half, right? So basically what you want to do is multiply this, step function by half. And you end up with this 1 over 2j, right? So once you got this 1 over 2j taken care of, now all you need to do is take care of that pi over 2 delta of omega. Now, you're probably on an exam, you're thinking, wow, how do we do this? How is this possible? Then, think simply. Realize that you can find an expression that gives you a delta function, right? A delta frequency signal. So you have to realize that using your properties, 1 is equal to 2 pi delta of omega. Now, how is this helpful? Well, you get the delta of omega that you need, correct? Basically, all you're going to be dealing with here is subtracting things. This pi over 2 delta of omega. Now, what you want is negative pi delta of omega. And the only way you can get to that form is if you subtract this by 3 halves pi delta of omega. Now, using math, you know that 3 halves pi of delta of omega is equal to 3/4, right? In the time domain, 3/4 is equal to, in the time domain, 3/4, in the frequency domain is 3 halves pi over pi delta over delta of omega. So basically all you're going to do is subtract your 1 half u of t minus 3/4. In the frequency domain, you get that expression, and that's pretty much it. After you do all this, you end up with your final expression for x of t, and that solves the entire problem. Now here, you have a signal being passed through two systems, right? You have this x of t equal to e to the minus u of t being passed through system h1 of t, and then being passed through another system, h2 of t. h1 of t is e to the minus 2t u of t. h2 of t is e to the minus 3t u of t. And you're asked to compute the output of this, right? So basically what you want to realize that is when you pass a signal through a system, this is equivalent to convolving these signals. So basically, you're convolving every signal that passes through, right? So what you want to realize is the inverse Fourier the Fourier transform of these signals are actually pretty well known. So when you convolve in the time domain, in the frequency domain, it's just multiplication. So using our properties, we pretty much already know the Fourier transforms of all these signals we're given here, right? So basically what you want to start off with is just finding out the output outside of this first system, h1 of t. And then after you find that output, then you shift it to your second system, h2 of t. Now here, x1 of t is equal to x2 of t convolved with h1 of t, which is equal to the multiplication of their frequencies. And you end up with this expression. Normally I would keep it in this form, but if you want to take the next level, be a bit more complex, then you'd probably want to express this expression into something bigger. like 1 over j omega squared plus 3j omega plus 2. But it's a bit beneficial to keep it in the form 1 over j omega plus 2 times 1 over j omega plus 1, right? So this gives you the output of the first signal being shifted to the first system. Now you want to shift this output to the second system, and that will give you y of t. Now realize that shifting it in the time domain just means it's convolving, right? You're convolving it in the time domain. So this means that you're going to have to multiply it in the frequency domain. So this is just simply multiplying the inverse for the Fourier transform of h2 of t by your expression. So basically y of j omega is x1 of j omega, which is the output of the first system, times h2 of j omega, which is the Fourier transform of h2 of t. And here you recognize that you're just multiplying 3 expressions. Now, technique here is to use partial fraction decomposition again to get into 3 independent expressions where you can find the coefficients and in turn find the inverse Fourier transform simply. Now, with this said, what you want to do is multiply the denominator over, and you'd end up with an expression for A, B, and C, right? So you get 1 is equal to A j omega plus 1 times j omega plus 2 plus j omega b j omega plus 2 times j omega plus 3 plus c j omega plus 1 times j omega plus 3. Now I'm going to let you solve for these coefficients, but here they are. You get a equals 1/2, b equals 1/2, and c equals -1. This could be a little exercise for you to work on. But once you do get your coefficients, you plug them into your expression that you had up there, and you get 1/2 over j omega plus 1 plus 1/2 over j omega plus 3 minus 1 over j omega plus 2. Now, these are pretty simple to compute. You can find the inverse for Fourier transform of these pretty simply. You know, using the properties, you know, this is equal to 1 over 2 e to the minus 2 minus e to the minus 2t minus e to the 1/2 e to the minus 3t, all multiplied by a unit step function. Now this next part is asking if x of t is e to the jt, what's y of t? Now you don't want to reinvent the wheel here. You know that convolving in the time domain just means multiplication in the frequency domain, right? And you know that pretty much you're just multiplying the inverse, the Fourier transform of each of these by each other. So basically, all you want to do here is find the Fourier transform of x of t and multiply it by the two systems that you end up with, the two systems that you're convolving through, right? So this is your x of j omega, which is equal to 2 pi delta of omega minus 1. Now, what you want to do is, since you're convolving through these systems in the time domain, you're basically just multiplying in the frequency domain. That we know now. And let's call these two multiplications equal to z of j omega, just to make our life a bit easier. Now, the trick that you want to do here is there's no type of formula that pretty much gives you a straight answer from this. So what you want to do here is actually go through and do the integral. Use the actual formula of finding the inverse, right, for your transform. So you get this expression for y of t. You get 1 over 2 pi, integral from -infinity to infinity, 2 pi delta of omega minus 1 times z of j omega times e to the j omega t d omega. Now, if you look at this expression, first off, let's start off by canceling out the 2 pi's, right? 2 pi's go away. If you look at this expression, this is just an implementation of the sifting property. What you want to do here is, by using the sifting property, you're taking every omega that's in this expression and making it equal to 1. Basically, the sifting property allows you to do that. So everywhere there's a omega in this expression, it's going to equal to 1. And this gives you an expression of z of j1 times e to the j1t. This is the expression you end up with by using the sifting property. Now, all that's left to do is plugging in z of j1, plugging in omega equals 1 to the expression of z of j omega that we put together, and figuring out whatever y of t is. Now from this, it's pretty straightforward what y of t is. It's just e to the jt times 1 over j plus 2 times 1 over j plus 3. And that's pretty much all there is to this problem. That's all you need to do.